So I'm going to skip to this slide here, the distribution of rods and cones. Rods and cones are shaped differently. Rods are much larger than the cones are. The ends of them anyway. They're large and they're tubular. If you remember that cartoon I showed you, they're tube shaped. Whereas the cones are much shorter and tapered. They're not evenly distributed to the retina. So you can think of the retina kind of as a round sheet of tissue. It's a very delicate piece of tissue, but you think of it as a round sheet of tissue. And what you have to realize is that the rods and cones are not evenly distributed to the retina. The fovea is the part of the retina that has the most cones. It's entirely made up of cones. Okay, the fovea, this word here, the fovea, is the part when we move our eyes to focus on something. The fovea is where we're focusing our attention, right? So if you're reading, your eyes are positioning themselves so that the words are focusing right on the fovea. If you're looking at something, if you're looking at anything, the point that you're focusing on the most is focused on the fovea. So it has the highest concentration of cones to be able to collect the highest amount of light from the thing that you're focusing on. Outside of the fovea, as you move out from the fovea to the outer parts of the retina, there's rods and cones. But there's more rods than cones, right? There are more rods out there than cones. But you have to remember that on the fovea is the part of the retina where we focus when we're looking at something. That's the part of the retina that receives the particular image that we are focused on, and then the area around it is simply there to make up to fill in the environment apart from the things that we're focusing on. So right here, if you look, this is a cutaway section of the eye, right? So this eye is actually looking up, right? So here's the cornea, here's the lens, right? And then this is this empty space here. It's not empty. It's actually full of something called vitreous humor, a liquid. And then right along here, starting from this point here, whoops, sorry. Let me go back to the, oh, there we go. Let me get my little pen going here. Starting from this point right here, and then going all the way around to here, and then starting up again to here, is the retina. Now the fovea is located right here. The fovea is located right there. So whatever we're focused on, whatever light rays that we're focused on are focused just like this perfectly onto the fovea. Okay, so they're focused perfectly onto the fovea, which this isn't perfect, but it's close enough, right? It's actually somebody who would be nearsighted, right? But they're focused on the fovea, right? Now, over next to the fovea, just about maybe 10 degrees off from the fovea, is a blind spot. This is a spot that does not have any rods or any cones. And the reason this blind spot is there is because this is the point where all of the axons of the ganglion cells in your retina exit the eye. So there's no receptors here, there's just a bunch of cables, a bunch of axons that are gathering up and exiting the back of the eye to make their way into your brain. So right here, this point at which we have no this point at which the axons of all of the retina gather up and exit the back of the eye is called the blind spot. And you're typically not aware of your blind spot because your brain fills in the blanks throughout the day. But you do become aware of your blind spot when you do something stupid like accidentally pull out in front of somebody when you're driving because you didn't look close enough. If you pull out in front of somebody, you did a quick look. It may have been your blind spot. They may have been in your blind spot and you didn't see them. If you look at this chart here gives us a measure of how many receptors there are concentrated in the retina. So along the x-axis here we have the angle, and this is the degrees This is a measure of distance away from the fovea. So the fovea is considered a 0 point, and then you have 10 degrees away from the fovea, 20 degrees away from the fovea, all the way to 70 and 80 degrees of the fovea, which is indicated here on this drawing right here. So this is the 0 point, and then we have 20 degrees, 40 degrees, 60 degrees, 80 degrees away from the fovea. Notice at the 0 point, at 0 degrees, where the fovea is, we have the highest concentration of cones, which are indicated here by the red, right? And then as we move away from the fovea, we have a higher and higher, we start seeing a lower concentration of cones. So the concentration of cones goes down as we move away from the fovea, but look what goes up. The concentration of rods. And the rods sort of peter off here as we get closer to the edges, right? And then notice this big block here about roughly 15 to 20 degrees away from the I guess that's like 17 degrees off the angle of the fovea. We have the blind spot. There's no receptors there, so everything takes a dump there, bang, bang. And there's no receptors there because that's the point where the axons exit the brain. Some of the diseases that you can have of your retina, well, one of the serious ones that's not listed on this slide is something that anybody can get, and it's a detached retina. So if you ever get hit in the face really hard, or you get hit in the eye, and you start seeing flashes of light after you've been hit in the eye when you move your eye, that's very dangerous. That means you have a detached retina. So remember, the retina is a piece of tissue that is on the back of the eye, and it's a piece of brain tissue basically on the back of your eye. And if you hit your eye hard enough, that piece of brain tissue can become detached from the back of the eye and float around. That's a very dangerous condition because the retina is a very delicate piece of tissue. It's more delicate than a wet Kleenex. That's how delicate it is. So if you ever get that, go to the emergency room, and what they'll do is they'll do a laser surgery on you where they laser back the retina back into the eye. It's a complicated procedure. It's a very dangerous procedure, but it's better than going blind. If you don't get it taken care of, you will go blind because the retina will get torn up, swishing around in there in the water. Another disease that's listed here on this slide is macular degeneration. Macular degeneration is when the fovea dies. Basically, the fovea and the area around it die. So what you end up with is this, in the middle of your visual field is just a white stain. You can't see anything, right? A huge blind spot. Happens a lot in older people. Retinitis pigmentosa is a disease. It's a genetic disorder where the rods and the cones are destroyed. They die. So the rods die first, and all the pigments, actually it's all the pigments, they break down. The rhodopsin pigments break down, and then the cones in the fovea can also be attacked as well, and they can break down. And of course, in really bad cases of retinitis pigmentosa, you can go completely blind. This example here shows you two pictures, right? The first one on the left-hand side shows you what the world might look like to you if you have macular degeneration. We have this just this spot in the middle of your visual field where you can't see anything. You can obviously see that this is a very bad disease to have. And then this other slide here is what retinitis pigmentosa might look like. Let's see. Okay. How many rods and cones do we have? In each retina, we have about 120 million rods and about 6 million cones. The blind spot, like I said, is the place where the optic nerve exits the back of the eye. And we don't perceive it usually because the eyes work together with the brain to fill in that information. So our eyes are working together to move around, and our brain is working to fill in that spot so that normally we are not aware of the blind spot. Here's a very extreme close-up cartoon of what the blind spot looks like. These little purple and red cells here are the rods and cones. These are the rods and these are the cones, of course. Notice there's more rods out here than cones, which is what we would expect, away from the fovea, right? Remember the fovea is where all the cones are. And then notice how these ganglion cells, right? These little cells, millions and millions of them, they all send their axons in a bundle to the same place. And these axons all, oops, did it again, didn't I? There we go there. All right. I keep forgetting to switch to my pen. These axons from these cells here, these axons all travel and they exit the back of the eye. And since there's no receptors here, that creates a blind spot, which as I said before, your eyes work together and your brain works with you to fill that in so that you're not aware of it. One way you can be aware of your blind spot is in your book. If you look at Figure 213 on page 29, here's a little thing you can do where basically you stare at the plus sign. You hold the book and you stare at the plus sign, and you move closer. You keep staring at the plus sign, and as you move closer, as you move the image closer and closer to your face, while you're staring at the plus sign, that dot that's on the left-hand side should disappear. It's kind of cool. There's a process. Let me see. Let me show you. Let me see. So there is, yeah, I'll start here. Okay. So there's this phenomenon in, well, first of all, let me explain this. Rods and cones. The rods are specialized for night vision. So the rods and the way they're wired up to the rest of the retina, the rest of the brain, allow you to see at night. They're more light sensitive and work primarily at night. I should say in dark. Okay, the rods work primarily in the dark. Cones are specialized for light vision when there's plenty of light. Okay, and there's this process that we go through as we go from light to dark, where we adapt to the darkness. I don't know if you've ever gone to like the movies and you're outside in the bright sunlight, and then you go into the movie theater. It takes it takes about 20 minutes for your eyes to adjust to the darkness. At first, you can't see anything in the theater, but then as your eyes adjust, you start to become to see. It gets easier and easier to make things out in the theater. This is dark adaptation. And then, of course, once your eyes have adapted to the dark, and if you've ever gone out into the bright light, you're like, "Oh my God," it hurts, right? Because your eyes are overwhelmed, so you have to readapt. Your eyes have to readapt to the brightness. But there's a lot of ways that we can detect this dark adaptation curve, right? There's some experiments that are done, and the way these experiments are done is pretty straightforward, right? So first of all, the observer is light adapted. So the observer sits in a room that's well lit for a while, so that his cones are pumping out, they're working like crazy, and the rods aren't doing much, right? Because the rods are washed out with too much light, and so they're not doing anything. But the cones they're less sensitive to light than the rods are, so they're pumping away, right? Then the light's turned off. Click. And then we let the observer dark adapt. So we let the observer sit for about 20 minutes for their eyes to adapt to the light. And then the observer adjusts the intensity of light. Remember we talked about how you can adjust, how you can measure thresholds by adjusting the intensity. And then what we do is say, okay, I want you to turn this knob on this light until you can just barely make the light out. And say, oh, I can see it now. Okay, so we measure the threshold in the dark after they're dark adapted, right?